Hello everyone, my name is Srilakshmi Krishnakumar and today I'll be presenting a project titled GP Diabetics Classifier. This project is actually part of our CS 6271 Evolutionary Computation and Humanoid Robotics module here at the University of Limerick. Our project is all about predicting whether a person is diabetic using GP, which is genetic programming. So let's dive into the details of this exciting project.
Hi, myself Ashita. I'm also working on this project and I'll be continuing the presentation from here. In this project, we aim to predict diabetes using reduced version of diabetes dataset utilizing genetic programming for classification tasks. Our primary objective is to develop an efficient classifier that performs well with this dataset while also exploring the capabilities of evolutionary algorithm. The motivation for using genetic programming is its ability to generate transparent tree-like models that evolve over time through natural selection processes. It's bio-inspired approach that can uncover complex patterns in the data. Now I'll take over from here and continue with the topic. Our dataset consists of various health related features, including variables like high blood pressure, body mass index, whether the individual is a smoker, and more. The target variable we are predicting is whether the individual has diabetes, represented as 1 for yes and 0 for no.
Hello everyone, this is Srilakshmi. So we have performed a series of pre-processing steps to clean the data, including handling missing values and addressing outliers. So the two important pre-processing steps we are focusing here are feature engineering and feature selection. Initially, we created interaction terms using polynomial features. So this allows us to combine features to capture relationship between them. Next, what we did was we applied feature selection using the variance threshold method. So what this does is that this removes features with low variance. In other words, features that don't change much and aren't useful for distinguishing between different classes. So by doing this, we reduce the number of irrelevant features and make the model more efficient. It's also important to note that normalization hasn't been applied here. This is because in this case, the models we are using don't require features to be on the same scale. Hello, this is Srilakshmi continuing. Let's see what genetic programming actually is. It's actually a type of evolutionary algorithm that evolves solutions, actually in the form of tree structures. Let's think of it as a process inspired by nature, where solutions compete and improve over time, much like survival of the fittest. What makes GP unique is its ability to mimic natural selection. It starts with a population of random solutions, evaluates how good they are, and then uses processes like crossover and mutation to generate new solutions. These newly generated solutions are actually better solutions. Over generations, these solutions evolved to become more effective at solving the problem. Now let's see why GP is so useful. The solutions it generates are like tree structures, which are transparent and easy to understand. GP is great at finding solutions in tricky nonlinear problem spaces where traditional methods might struggle. It can also be applied across domains like classification, regression, and even optimization problems. So, in essence, GP is like a creative problem solver that improves with each iteration and produces solutions we can trust and understand.
For this implementation, we use the deep library, which is a powerful Python framework for evolutionary algorithm. It helped us to design and execute genetic programming processes. Our GP setup involved configuring several parameters such as population size of 1000, a crossover probability of 80%, and a mutation probability of 25%. We also ran the algorithm for a maximum of 100 generation to ensure enough time for convergence. The tree structure of the individual was constrained with a minimum height of 3 and a maximum of 50 to control the complexity of the models. Additionally, we set a random seed to ensure the results were reproducible. By iterating over generations, our GP evolved progressively better solutions for diabetes classifications.
Hello, this is Srilakshmi taking over. Before we could even start running the genetic programming, we had to get our data and framework ready. So let's start with the data preparation. Initially, we split the dataset into training and testing set. This actually ensures that we can evaluate how well our model generalizes to unseen data. We converted the data into NumPy arrays, which is essential for compatibility with the deep library which we used for GP. Now let's dive into the GP framework setup, where the real magic happens. A key part of GP is the fitness function, which is like a coach for our model. For this project, the fitness function was designed to maximize the classification accuracy. Each model in GP is called an individual and it's represented as a primitive tree. This tree contains functions and features and it's evaluated based on how accurately it classifies the data. By defining this setup, we created a system where models evolved over generations, becoming more and more accurate as they learned from their performance. It was amazing to see how this evolutionary process turned random initial guesses into well performing classifiers.
This is Hashita, and I will continue with the next part of the topic. For the GP to work efficiently, we needed to define the function set and terminals. The function set included basic arithmetic operations such as addition, subtraction, multiplication, and safe division. These allowed the trees to perform mathematical operation on input features. The terminals were simple constant values 1 and 0, which were used as building blocks in the GP trees. These operations and terminals formed the basis for models that evolved throughout the generations.
Hi, this is Lakshmi here. Once we define the function set and terminals, we set up the GP toolbox. This is where the evolutionary process starts. We use the half and half initialization method to generate initial GP trees, ensuring diversity in population. From there, the algorithm proceeded through several evolutionary steps like selection, crossover, mutation, and evolution. Selection was done using tournament selection, which helps ensure that the best candidates are chosen to reproduce. Crossover and mutation operators help generate new individuals, and the fitness evolution was based on the classification accuracy. Throughout the process, we tracked various statistics, including average fitness, minimum and maximum fitness, as well as the standard deviation. The best individual model from each generation was saved in the Hall of Fame for later evaluation and predictions. The best model from the final generation was selected and used to predict the outcomes on the test dataset. We saved these predictions in a CSV file for further analysis. Now let's look into the results. Our results demonstrated significant improvement as the GP algorithm progressed. Initially, the model started with a relatively low accuracy of around 60.7%, which is typical for randomly generated solutions in the first generation. However, through evolutionary processes like selection, crossover, and mutation, the model gradually became more refined. By the 100th generation, the best performing model, it reached an accuracy of about 74.5%. This showcases a substantial improvement of nearly 14%. We also observed a reduction in standard deviation across the generations. This indicated that the population was converging towards an optimal solution. The best model from the final generation was selected for evaluation on the test dataset. Finally, the predictions made by this optimized model were saved in a submission CSV file for analysis and evaluation.
This is Harshita, and I'll now continue with the next part of the presentation. We can see that the performance growth has been increased from 60.7% to 74.5% over the 100th generation, starting with 60.7% in the 0th generation and reaching around 72.4% in the 50th generation, and it reached around 74.5% in the 100th generation. The standard deviation decreased, indicating the population converged to optimal solutions. The final model generalized well to test data, demonstrating the effectiveness of the genetic programming.
Hello, this is Srilakshmi here. we have come to the conclusion. To wrap up, we used GP to build a classifier for predicting diabetes. By iterating through generations, we improved accuracy from 60% to 74.5%. This project gave us hands-on experience on evolutionary algorithm and reinforced the value of interpretable models in healthcare. Moving forward, we could experiment with larger dataset and additional tuning to push the model even further. Thank you for listening.